Hello, welcome back. Let's continue on learning about rotational motion. Let me share my screen. So the last video, we just kind of covered the basics of rotational motion, in particular rotational kinematics. We just described the motion of something that is rotating about an axis, but we didn't describe why the object starts to rotate to begin with. And so that's what we're going to focus in on today. What are the causes of rotational motion? Let me share my screen. The objectives for this lecture will be to help us define and calculate torque in various situations, define rotational inertia or moment of inertia, and state Newton's second law for rotational motion and use that to solve problems. So rotational motion has many applications in our everyday lives, as you can see in things involving gears and motors, and engines, and even the simplest case of a seesaw. We can apply rotational motion to a seesaw. So we're going to learn how to do that in this lecture today. So far, just to remind you what we've talked about and kind of give you a little preview of what we will be focusing on. We talked about rotational kinematics. So in linear motion, we learned that an object can move a distance d, right? It can have a velocity v, it can have an acceleration a. And in rotational motion, we learned that there's a rotational analog for all of these variables. When an object rotates, the distance that it rotates through can be described by the angle theta. The object can have a rotational velocity omega. And the object, if it's speeding up and it's spinning or slowing down and it's spinning, it can have a rotational acceleration, and we call that alpha. The amazing thing about rotational motion is that the analogies go on even further. So in linear motion, we learned that for an object to experience acceleration, it must have a net force acting on it. In rotational motion, the thing that causes the object to rotate is called a torque. And that's denoted by this funny looking T symbol, tau. And we're going to define what we mean by torque in the next few slides, but just know that you need a torque to cause something to have a rotational acceleration, just like you need a force to cause something to have a linear acceleration. Now, Newton's second law told us that the net force acting on an object is equal to its mass times its acceleration. So in linear motion, we had to take into account the mass of the object to determine its acceleration as well. In rotational motion, it's a slightly different concept. In rotational motion, the equivalent to mass is what we call moment of inertia or rotational inertia. And we denote that with the letter I for moment of inertia. So we're going to learn about the relationship between the net torque acting on an object that's spinning, its rotational acceleration, and its moment of inertia or rotational inertia. That's the focus of this lecture today. And these are all of the analogs between linear motion and rotational motion that we're going to learn so far. So let's get into it. What is a torque? Okay. A torque is the product of a force and a distance from the fulcrum. By fulcrum, we mean the axis of rotation. So it's related to force, but we also have to think about the distance from the fulcrum or axis of rotation. So torque is the force multiplied by L here, and by L we call the lever arm. So say, for example, I have a wrench, right? Here's the end of the wrench. I'm trying to turn a bolt or nut or whatever it's called. And here's the wrench handle. As all of you might have experienced in your everyday life before, if I want the best chance to rotate this wrench, I have to apply a force all the way out here on the end. The lever arm here would be the distance L from the axis of rotation, where the bolt is, out to where the force is being applied. If I try to apply the force closer in, I'm not going to get as much torque, and I'm not likely to rotate the bolt. Lever arm we define to be the perpendicular length from the axis of rotation out to the line of action of the applied force. So in this case, the lever arm is the full length of the wrench. However, if I apply a force on a slightly different angle, my lever arm changes. So here's my wrench again. Let's suppose I apply a force at an angle. Can you visualize that this is going to be less torque here? I'm not going to get as much torque acting out. My lever arm here is the distance from the axis of rotation out to the line of action. The line of action is like a line drawn through the force. So here the line of action is going to be right here. My lever arm is the perpendicular distance from this line of action to the point of rotation right here. My lever arm has become shorter now, so I don't have as much torque. In the extreme case, right, let's say I've got my wrench. Here's my wrench, my very sadly drawn wrench here. And let's say I apply the force right here on the end like this. Is the wrench going to move at all? No, because there's actually no lever arm here. This thing is not going to rotate anything. Right? Not a very good position for trying to turn the wrench. Okay. So you can see that torque is a little bit tricky because you have to take into account the force and the length of the lever arm. The units for torque, since it's a force times a distance, it's a Newton multiplied by a meter. That's our units for torque. And as we mentioned, torque is the rotational equivalent to force. A net torque is what causes objects to rotate or have a rotational acceleration. If the net torque acting on an object is zero, the object will not rotate at all, or it will have a constant rotational velocity. If the net torque on the object is zero, it has zero rotational acceleration. If you remember, F net equals ma. If the net force acting on the object is zero, the acceleration of the object is zero. That means it's either at rest or moving at a constant velocity. The same thing occurs with torque. If the net torque acting on the object is zero, the rotational acceleration alpha is zero. That means it's either at rest, as shown in the left-hand fan right here, or it's moving at a constant rotational or angular velocity, as shown here on the right. Now, torques can either make the object rotate one way or the other, right? If I, push one way on the wrench, it'll rotate clockwise. If I push another way on the wrench, it'll rotate counterclockwise. We need to take that into account, right? So by convention, most textbooks use the convention that torques that produce a clockwise rotation are negative, and torques that cause a counterclockwise rotation are positive torques. It's kind of the same idea when you have two forces that are acting in opposite directions. You have to denote one of them with a negative sign to show that they're acting in opposite directions. Same thing with torque. If you've got two torques acting on an object, one of the torques is trying to make it turn clockwise and the other torque is trying to make it go counterclockwise, you have to take that into account. And you would call the torque that is making a clockwise rotation negative. And you would call the torques that cause a counterclockwise rotation to be positive. We'll practice this in a bit. Key takeaway here is that a net torque acting on an object causes it to have an angular acceleration. If the net torque acting on the object is 0, it's not going to have an angular acceleration. How do I calculate torque? Well, remember, if the force is perpendicular to the lever arm, as is shown here, the torque is simply the perpendicular force multiplied by the lever arm here. That's indicated by the letter D. By either increasing the force or increasing the lever arm, I can cause a larger torque, and it'll be more likely that I'll be able to turn this wrench. If the force is not perpendicular to the lever arm, we have to take that into account. See up here on the top picture in the top right-hand corner, we have a situation in which the force is not perpendicular to the lever arm. The force is being applied at an angle to the wrench. My line of action of the force is like right here. The perpendicular distance from the axis of rotation to the force line of action is this length right here. The lever arm, in this case, is going to be the length of the actual wrench, R, multiplied by sine of the angle theta. You can check that using some trig. If I take the sine of the angle, it's the opposite side over the hypotenuse, which is R. And so the torque here, remember, torque is force times lever arm. In this case, it's going to be force times the length of the wrench, which is R, multiplied by sine of theta. You can also think of R, the length of R is the distance from the axis of rotation out to where the force is being applied, right here. The bottom animation is really nice because it shows situations in which you have the most torque, right, and your force is completely perpendicular to your lever arm, and that decreases as you go the other way. So as he changes the direction of the force, he decreases the torque until it becomes 0, because there's no lever arm in this end point right here. So here's an example of how we can use torque to kind of solve some problems for us. So let's suppose we have a weight of 50 newtons placed a distance of 2 meters from the fulcrum of a seesaw. At what distance from the fulcrum should a weight of 30 newtons be placed on the opposite side to balance the seesaw? So this is a pretty big seesaw. Let's draw out our picture. Here's the seesaw, here's our fulcrum placed right in the middle. 50 newtons is placed a distance of 2 meters from the fulcrum. So from here out to here, I have 50 newtons of force being placed right here, 2 meters away. We want to predict or calculate where should I place 30 newtons on the opposite side such that the seesaw is balanced. My first question to you is to think, do I need to put the 30 newtons further away from the fulcrum than 2 meters or closer to the fulcrum? Make a prediction and then let's check our work with the mathematics. So we're going to apply Newton's second law here. Hold on. We're going to apply Newton's second law here, sorry. And in this case, since the seesaw is completely balanced, there's no angular velocity, there's no angular acceleration here. Right? Everything is balanced out. The seesaw is not rotating one way or the other, it's staying completely level. So in that case, the net torque acting on this seesaw has to be equal to 0 because the seesaw is balanced on both sides. There's two forces that are causing a net torque on the seesaw. There's one due to the 50 Newton weight and the other one is due to the 30 Newton weight. The torque due to the 50 Newton weight is causing the seesaw to rotate this way. Like if there wasn't a 30 Newton weight on the other side and I just placed this 50 Newton weight here, can you see that the seesaw would rotate downwards like this and it would be following a clockwise rotation. So we're going to say that the torque due to the 50 Newton weight is negative by convention. It's a clockwise torque, we'll call that negative. Then we have the torque due to the 30 Newton weight. If that was the only weight that was acting on this seesaw, it would make the seesaw want to rotate counterclockwise, right? If everything else was gone, this thing would rotate, this thing would make it rotate counterclockwise. So we'll call this torque positive. Those are the only two forces that are causing a torque on the seesaw. The force from the fulcrum does not cause a torque because it's placed right in the center of the seesaw and there's no lever arm. So when I sum these up, they have to be equal to 0 because the seesaw is completely balanced. Now remember, torque we said is equal to the force times the lever arm. The torque due to the 50 Newton weight is therefore going to be the force 50 newtons multiplied by the lever arm, which is the distance from the perpendicular distance from the fulcrum to the line of action of the force. In this case, it's 2 meters. The torque due to the 30 Newton weight is going to be the force that it's acting, which is 30 newtons, multiplied by the lever arm for the 30 Newton weight. We don't know what the lever arm is. That's what we're trying to determine. Where do I need to place it? Right? So we're solving for L for this one. The sum of these has to be equal to 0 because the seesaw is balanced. So this is going to be negative 100 Newton meters. This is going to be 30 newtons multiplied by L. And from here, it's some algebra. "30 newtons multiplied by the lever arm L is equal to 100 Newton meters. Divide both sides by 30, and you get that the lever arm is equal to 3.3333, repeating, meters. Is that a good expectation of where it should be? Well, since it's less weight, in order to balance out the other weight on the other side, which is more, it has to have a longer lever arm so that the torques on each side are equal and opposite. So it should be a little bit further away, and that's what we got. 3.3 meters is further away than the 50 Newton one at only 2 meters. We need a really big seesaw for this to happen. Concept question for you. Using a screwdriver, you try to remove a screw from a piece of furniture, but you can't get it to turn. To increase the chances of success, you should use a screwdriver that has a narrower handle, is longer, is shorter, or has a wider handle. Think about it for a second, pause the video, make your prediction, and then we'll check it together. The correct answer here is that the screwdriver should have a wider handle. If I look at the screwdriver like head on, right, here's this, the screw in the wall, and I'm trying to get it to turn this way, I need to increase the torque to get this thing to turn. And in order to do that, I need to use something with a wider handle. Right, so if I draw my handle now, kind of looking at this thing head on, if I apply a force over here on the handle, here's my lever arm. This is going to give me a pretty big torque, right? If I make the handle even wider, very bad drawing, but let's say I put, I try to turn it. Here's my force over here. Here's my lever arms even bigger. It's going to give me more torque to be able to turn it. So wider handle would be your best bet there. Let's focus now on rotational inertia. We said that the rotational equivalent for force is torque. The rotational equivalent for acceleration is angular acceleration. The rotational equivalent for mass is moment of inertia. Okay, so if I put these all together, we already learned Newton's second law is F net equals ma. So therefore, you can imagine for rotational motion, the equivalent for this is going to be that the net torque acting on the object has to be equal to moment of inertia I multiplied by rotational acceleration alpha. This is Newton's second law for rotational motion. Question is, what do I mean by rotational inertia I? Rotational inertia, which we denote with the letter I, is also sometimes called moment of inertia, and it's just like mass in that it's the resistance of an object to change in its rotational motion. Like mass, it was like the inertia of the object. More mass was harder to get it to accelerate, right? Rotational inertia is the resistance of an object to change in its rotational motion. So it's harder to get it to start spinning, and it's harder to get it to slow down. The units for rotational inertia are actually a kilogram multiplied by a meter squared. We're not going to get into the details of why this is, but the important thing to know about this is that the rotational inertia depends upon the mass of the object, but it also depends upon how the mass is distributed about its axis of rotation. So that's why there's a meter squared here, because it depends upon how the mass is distributed about the axis of rotation. So different shapes, like differently shaped objects, are going to have different rotational inertias. And even for the same object, they can have different rotational inertias depending upon where the axis of rotation is put. A rule of thumb is that when the mass of an object is concentrated towards the center of the object about its axis of rotation, the rotational inertia of the object is small. When the mass of the object is concentrated towards the edge, far away from the axis of rotation, the rotational inertia is large. And that would mean it's difficult to get this thing to start to spin or slow down in its spinning. It makes sense when you visualize it. So here on the next slide, here's the visualization. So here's several different objects, right? Right here, no, don't look at the T-bot, that's complicated. For right here, let's say we have a solid disk of mass m. And let's suppose we have a solid hoop, a hoop also of mass m. Both of these have the same mass and they both have the same radius. The radius is the radius of the object. Notice that the disk has more mass concentrated towards the axis of rotation right here in red. The hoop has a lot of all of its mass concentrated further away from the axis of rotation. So it's more on the periphery. The disk has a smaller moment of inertia than the hoop. For the same mass and radius, the disk is going to have a smaller moment of inertia because there's a 1/2 out here. We're not going to explain how they got these values. It involves calculus. But just notice that the disk has a smaller moment of inertia than the hoop because there's more mass concentrated towards its axis of rotation. That means it's easier to get this disk spinning, and it's easier to get this disk slowing down in its spin. Again, if you look at the spheres here, we have a solid sphere on the top versus a hollow sphere on the bottom. The hollow sphere is going to have a larger moment of inertia than the solid sphere for the same mass and radius. Last little figure here shows like a kind of just like a line of mass. And if it's spinning in the middle, the moment of inertia is 1/12 times its mass times its length squared. Notice for the same object, for the same distribution of mass, but if I rotate it on the end, the moment of inertia gets bigger, right? So even for the same object, I can have different moments of inertia depending upon where my axis of rotation is as well. You don't have to memorize these formulas. You can always look them up in a table online. They're also in your book. Key takeaway is that the moment of inertia depends upon how the mass is distributed about the axis of rotation. And so that brings us back to Newton's law for rotational motion. We've now defined everything we have. We've defined torque, we've defined a moment of inertia I, and we've defined angular acceleration A, alpha. And so as the net torque on an object increases, the rotational acceleration of the object will increase, right? Similarly, as the rotational inertia increases, the rotational inertia acceleration is going to go down if the net torque remains constant. A side friendly reminder that to use the equation net torque is equal to I times alpha, you have to make sure that alpha is in radians per second squared. So I wanted to pause this and be able to allow you to make a prediction about which one's going to get to the bottom first. But the little animation just goes automatically, so I couldn't pause it. But notice that you've got a solid disk, a hollow hoop. You have a solid sphere and a hollow sphere. Notice that the solid sphere gets to the bottom first. The reason being is that the sphere has the lowest moment of inertia of all of them. And so it's easier to get it to accelerate, have a rotational acceleration. Its moment of inertia is the smallest for a solid sphere. For the solid sphere, let's go back. The moment of inertia was 2/5 mr squared. And the next one that reaches the finish line, it looks like it's the solid disk, right? So the solids are reaching the bottom first. The moment of inertia for a solid disk is 1/2 mr squared. The next one that reaches the bottom is the hollow sphere. Its moment of inertia is this 2/3 mr squared. And the last one, the loser here, is the hollow disk or the hoop. And its moment of inertia is just mr squared. So notice that as you go up this, the moment of inertia increases. That also means that the angular acceleration alpha is going to decrease. It's more difficult for an object that has a higher moment of inertia to accelerate and start spinning versus an object with a lower moment of inertia. It's easier to get it spinning and moving and accelerating. So the next time you go to the Science Center and they show you this experiment, you can explain why that happens. One more concept question for you. Choose all of the following statements that are correct. An object that has no rotational acceleration has no torques acting on it. An object that has two equal and opposite torques acting on it must not be rotating. As the rotational inertia of an object is increased, it will become easier to make the object have a rotational acceleration. Under the same net torque, an object with its mass concentrated at its center will have a smaller rotational acceleration than an object with its mass concentrated at its edges, assuming both objects have the same mass. Pause the video, think about each of these statements for a second, decide which ones you think are correct, and we'll talk about it next. There's actually none of these are correct. Whoops. An object that has no rotational acceleration has no torques acting on it. This is false because all this, if it has no rotational acceleration, all that tells me is that the net torque acting on it is 0. There could be two equal and opposite torques acting on it that sum up to 0, so it still has torques acting on it. It's just that the net torque sums up to 0, and so therefore it has no rotational acceleration. An object that has two equal and opposite torques acting on it must not be rotating. Okay, that means that the net torque on it is 0. That also means that the angular acceleration of it is 0. Does that mean that it's not rotating? No, it either has a rotational velocity of 0 or its rotational velocity is constant if the angular acceleration is 0. As the rotational inertia of an object is increased, it will become easier for the object to have a rotational acceleration. That's false. You saw on that little animation that as the rotational inertia goes up, it's slower to start in its spinning, and it's slower to have it has a slower rate of rotational acceleration. Under the same net torque, an object with mass concentrated at its center will have a smaller rotational acceleration than an object with mass concentrated at its edges. If there's mass concentrated towards the center, kind of like the disk situation, that means the moment of inertia is small. If it's got a net torque acting on it, that means its angular acceleration is going to be big. If an object has its mass concentrated on the edges, kind of like the hoop, the moment of inertia is big. If there's a net torque acting on it, that means that its angular acceleration is going to be small. So none of the above, sorry. I guess it was a trick question. None of them were right. Let's practice this using a little bit of math for our last practice problem. A merry-go-round has a rotational inertia of 800 kilogram meters squared and a radius of 2 meters. What torque is required to give the merry-go-round an acceleration of 0.05 radians per second squared? I've got that the rotational inertia I is 800 kilogram meters squared. Its radius is 2 meters. Its angular acceleration is 0.05 radians per second squared. And I'm looking for the torque required. Let's use Newton's second law for rotation. Net torque is equal to I alpha. Moment of inertia I is 800 kilogram meters squared. Angular acceleration is 0.05 radians per second squared. The torque required to cause this angular acceleration is 40. And you can check the units later, but the units come out to be a Newton multiplied by a meter. Another question for you. What force would be required if I was going to apply a force on the edge of the merry-go-round? What would be the force required to make this torque happen? So if I do a bird's eye view of the merry-go-round, here's the merry-go-round. Its radius is 2 meters. Let's say it's rotating this way. Angular acceleration of 0.05 radians per second squared. The torque required to do that is 40 Newton meters. What's the force required to do that if I was applying a force on the edge of the merry-go-round? If I was applying a force out here, in order to get this thing to spin this way, I would apply the force right like this, perpendicular. And if you remember, the other definition of torque that we have is that it's a force applied multiplied by the lever arm. I know the net torque that I need to apply is 40 Newton meters. The force is what I'm trying to figure out. The lever arm here is the distance from the axis of rotation, which is right in the center of the merry-go-round out to the edge, which is 2 meters. So the force I would need to apply here is 20 newtons right here on the edge. So that's a quick crash course in rotational motion and causes of rotational motion. The relationship between net torque, angular acceleration, and moment of inertia. Catch up with me on the next video in which we will talk about angular momentum.